Hello, good people. Welcome to video number 2 here of the Taylor series, Maclauren series, and building series that are equivalent to maybe not so nice functions. And here's a not so nice function. I have a rational function 1 over 1 minus x. We're going to build a Maclauren series for 1 over 1 minus x. Let's see what that looks like. In order to do that, I kind of need to see what the pattern is. So I'm going to do a couple of derivatives here. And maybe this time, let's go out to 5 derivatives. By the way, after the 3 primes, then it just becomes a little number in parentheses, right? So that way we don't end up with a bunch of primes. Okay, so let's find the derivative of these. The derivative of 1 over 1 minus x, well, it might be helpful if I write it like this, and then I can take the derivative. So that'll be negative, using the chain rule, times the derivative of the inside, which is negative 1, which is positive 1 minus x to the negative 2. Okay, and then I take the derivative again, using the chain rule. Negative 2 times 1 minus x to the negative 3 times negative 1, because I'm taking the derivative of the inside, and then that's going to be 2 1 minus x to the negative 3. Take the derivative again. Negative 6 1 minus x to the negative 4 times negative 1. Well, that's 6. Now, wait a minute. Have we seen these numbers before? Negative, I'm sorry. And then multiply, that would be negative 24, 1 minus x to the negative 5 times the derivative of the inside, and that's positive 24. Really, I'm just getting factorial coefficients here, right? And they're always positive, in case you hadn't noticed. So therefore, this is going to be negative 120 times 1 minus x to the negative 6. I'm sorry, I missed some. No, that's right. Negative 6 times negative 1, and that's 120 times 1 minus x to the negative 6. Okay, I found my derivatives. Now what do I do? Well, I'm supposed to find the derivative at my center. But my center, because this is a Maclauren series, my center is 0. So I'm supposed to plug in 0 wherever I see an x. Okay, so this is f of 0 is, plug in a 0, that's just 1. F prime of 0, substitute a 0. Oh, I'm sorry, this is not 0. This this is not 1, it's 0. Okay, I'm having a brain fart. Substitute a 0, 1 minus 0 is 1 to the negative 1, that's 1. Substitute a 0, 1 minus 0 is 1 to the negative 2 is 1. And then from here on out, really, all of these are going to turn into 1. So then this is just 2. The third derivative is 6. The fourth derivative is 24. The fifth derivative is 120. Because 1 minus x to the any power is going to, when I substitute 0, is just going to be 1. Oh, well, that turns out to be nice. Great. So now let's see how this is going to look when I write it out. So I have 1 over 1 minus x is going to equal the first term plus the derivative times x minus c. Oh, but my c is just 0, so really it's just that, plus 2 times x minus 0, which is that, squared divided by 2 factorial, plus 6 times x minus 0 to the third divided by 3 factorial, plus 24x to the fourth divided by 4 factorial, plus 120x to the fifth divided by 5 factorial, and so on, plus dot, 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 right? We continue going forever since we're building an infinite series, a Taylor series. In this case, a special case, the Maclauren series. Well, can I simplify? This be still 1. This is x. Well, wait, 2 factorial is 2 times 1. That's 2. These are going to cancel. So I'm just left with x squared plus 3 factorial is 3 times 2 times 1, that's 6. Oh, these are going to reduce. So I'm just left with that plus 4 factorial is 24. Oh, look at this. And then 120 divided by 5 factorial. 5 factorial is 120. So I'm left with x to the fifth plus dot, dot, dot. This is my Maclauren series for 1 over 1 minus x. Can we write it in summation form? Sure. Starting at 0, going to infinity, what's the pattern? Well, it looks like it's just x to the n, right? If this is 0, plug in 0, x to the 0 is 1. If this is 1, x to the 1 is x to the second. When I plug in 2, x to the 3. Yes. Nice. All right. So then the question is, when does it converge? So we go to the ratio test. The limit as n approaches infinity of the absolute value of the n plus 1th term divided by the nth term, and we're going to see when that is less than 1. We want it to converge. Well, this is the same thing as the limit as n approaches infinity of x to the n and x to the n are going to be canceled out, so I'm just left with x. And as n goes to infinity, well, there's no n's to grow, so then this is just that, and I want to know when it's less than 1. Well, this is true. This is true if x is between -1 and 1. But when I have a starting and ending point to my interval of convergence, I need to check the endpoints. So let's check the endpoints. If x is -1, then my series is going to look like this. Well, this is an oscillating series, right? Plug in the 0, it's 1. Plug in 1, that's going to be -1, +1, -1, +1, -1. This diverges because it never approaches a number. And if x equals +1, then I have 1 to the n, and that's 1 plus 1 plus 1 plus 1, and I know that diverges. So therefore, my interval of convergence, the only x values where this function is equal to this is, or are, x values that are between -1 and 1, but not including -1 nor 1. I found my interval of convergence. So, are we always going to have to do this business? No. And if you do, you certainly don't have to go up to the sixth derivative. Most of the time, they're going to tell you, hey, can you go to the third degree Taylor polynomial or third degree? So you don't have to do that. Are you going to have to make your own series? Well, no, because if you move on, it gives us what the series is for each of these functions. Notice the little hearts. Those are the ones that you should memorize. I'm going to say that again. Those are the ones that you should memorize right off the bat. And I want to, like, you should know them cold. And I want to point out these particular ones. Notice that e to the x is equal to this Taylor series for all x values. And sine of x is equal to this Taylor series for all x values. And cosine is equal to this Taylor series for all x values. 1 over 1 plus x is equal to this series for x values between -1 and 1. So we got that. But the moral of the story is, what we're saying is you can approximate a trig function or an exponential function by just taking an infinite number of terms, which we call a power series, which we built as the Taylor series. It says, you are strongly encouraged to memorize a series marked with a heart. They are commonly featured on the AP Calculus exam. And here's why you're going to need to memorize them. In the next set of videos, we're going to talk about how if you know what the Taylor series is for e to the x, then you'll be able to know what the Taylor series is for e to the 3x squared. They look alike, but not, they look similar, but they're not alike. And yet, if I know what e to the x is, I'll be able to find the Taylor series for this. Or if I give you uh, the Taylor series for the natural log, you'll be able to take a derivative and figure out the series for the derivative of the natural log, or any of these. And so the videos that are coming up, the series of videos that are coming up are going to tell us how we can use the Taylor series when we're looking for, I guess, variations of a series that I know. And we'll talk about that here in a little bit. But the takeaway from this section is we need to memorize these four series for sure. You need to know them cold, because knowing them are going to save you time when you're asked to do something like this.